Hello, in this video we will be looking at exponential functions. By now you have probably encountered a number of different types of functions. Polynomial functions such as f of x equals x plus 3, which is a linear function. Quadratic functions like y equals x squared. Cubic functions, quartic functions, and so on. If you're studying A-level mathematics, you would have learned how to sketch these types of functions and transform them, differentiate them, and integrate them so far. You've also looked at trigonometric functions like cosine and sine and tan, theta, and rational or reciprocal functions like f of x equals 1 over x. These are all very useful in many different contexts. For example, in my video on modeling with differentiation, we used a cubic function to find the maximum possible volume for a given the given dimensions of a particular box. So now we're going to add to this tool set with exponential functions. So let's go ahead and look at some examples, and let's see what exponential functions are, and then maybe go through some example problems as well. Okay, so let's draw up an axis here, x-axis, and let's call this one f of x. And let's have a look at some examples of exponential functions. Okay, so you could have something like f of x equals 2 to the x. This is an exponential function because the unknown is in the exponent. If you look at polynomials, if you remember the definition, this included that all powers or exponents were positive integers. So polynomials, they cannot have an unknown in the exponent. For trigonometric functions, the unknown is within the trigonometric function itself. So the theta is within the sine function. And rational functions, the idea there is it is a fraction of two polynomials. Okay, so you can have a polynomial on the top of the fraction and a polynomial on the bottom. And that's what defines a rational function. So exponential functions are different in that way. They have the unknown in the exponent. So you could also have something like 10 to the x plus 3. That's also an exponential function. You could have f of x equals 3 to the x plus 5. That's also an exponential. And you could have something like f of x equals 2 multiplied by 4 to the x. That's another example. In general, these have the form f of x equals a multiplied by b to the x plus c, where a, b, and c are all constants. Okay, so looking at this example here, 3 to the x plus 5, if this was 5x, it's no longer an exponential function. It becomes a bit more complicated, and it becomes a different type of function then. Okay, so let's have a look at f of x equals 2 to the x, and let's have a go at plotting it on this graph and see what it looks like. So I want to draw my scale on the x-axis. So this might be like this: 1, 2, 3, 4, let's go up to 5. And then on the y-axis, I want my scale to be much larger. So I'll go up by 5s. So something like this: 5, 10, 15, 20. And let's do our table of values down here. So let's draw a quick table. And on this one, I'm going to start at x equals 0, and we'll do x less than 0 later on. So starting at x equals 0, 2 to the 0 is 1. So we're going to get a point at 0, 1. When x equals 1, 2 to the 1 is 2. When x equals 2, 2 to the 2 is 4. When x equals 3, 2 to the 3 is 8. When x equals 4, 2 to the 4 is 16. Then 32, then 64. We'll go up to 6, but we won't be able to plot all of that. Okay, so let's plot the points, and then maybe you'll notice, have a few things you've noticed already about about this function. So we've got our initial point at 0, 1, about there. 1, 2 might be about there somewhere. 3, 8. 2, 4. Almost forgot that point. 2, 4, about there. 3, 8, maybe up here. 4, 16. That was, I didn't actually label the axis, did I? 2, 3, 4, 5. And then this was 5, 10, 15, 20. That makes things easier. Okay, so 4, 16 is about here. And 5, 32 is, well, I can't fit that on the graph. Somewhere up here. Okay, maybe about there. All right, so now let's see if we can trace that in. I'm going to start here. Okay, not too bad. And that keeps going up there, and that is f of x equals 2 to the x. Okay, not too bad. Okay, so is there anything you noticed? The first thing I would probably point out is that we can see that we're doubling the y value each time. So we start at 1, double that, 2, double that, 4, 8, 16, double 16, 32. 32 times 2, 64. So that's one feature of this function, 2 to the x. It's kind of like the doubling function, if you like. Something else you might notice is it grows really fast. Even though we drew our scale, our x scale really stretched out, so we've only got 5 points on our x-axis here, and we got up to 20 on our f of x scale, still we couldn't even fit the 6 point on. So exponential functions grow really fast. That's what's called exponential growth. And that's kind of something that these other functions don't really capture in the same way. That's something, you know, unique and powerful about the exponential function, being able to capture that type of growth. And there's actually an old story about this particular function. Supposedly it's about the inventor of the game of chess. He was a humble farmer, and his king asked him to come to his court to teach him how to play this game. And the humble farmer went to the court and taught the king how to play the game of chess, and the king was so impressed. He said, choose your reward. I love this game so much, you can decide how I should reward you. And the farmer says, I'm just a humble man. I just want enough food to feed my family, so just enough grains to fill the chessboard. Secretly, the farmer knew that the king was a little arrogant and not too good with numbers. So he said to the king, yes, just enough grain to fill the chessboard in this way. So on the first square, put 1 grain. On the second square, 2 grains. On the third square, 4 grains. And so on. So the fourth square, 8 grains, and 16, then 32. So doubling the amount of grains on the squares. The king was a little taken aback, and he says, what, is that all you would like? Surely you don't want a bag of gold or something like that? And the farmer says, no, that's enough for me, thank you. The king tells him that's fine. He sends the farmer away, sends for his treasurer, and tells him to collect the reward for the farmer and send it off to him. A week later, the farmer returns to the king's court and asks the king about his reward. He hasn't received it yet. The king is outraged. He sends for the treasurer and yells at the treasurer, why have you not given this farmer his reward? All he wanted was a chessboard full of grains. And the treasurer says, we cannot possibly give him this reward. There's not enough grain in your kingdom to give to this man to fulfill the reward. And he points out to the king why this is. And the king thinks the farmer is so clever that he promotes him to his chief advisor. There's also another story that says the king was so angry at being tricked that he had the farmer executed, but I choose to believe he was so impressed with his intellect. So let's have a look then at why there was not enough grain in the kingdom. So if we continue to the 10th square, so let's put a few dots here. If we continue to the 10th square, if we keep doubling each time, this will be 1028 grains. Okay, still not too bad. If we continue to the 20th square, we are already in the millions. So this is 1,048,576 on the 20th square of the chessboard. If you go to the 50th square, you are in the quartillions. So this is approximately 1 quartillion. So that's not billions or trillions, but quartillions. If you get to the 64th square, I'm not sure what the name of this number is, but it's approximately 2 multiplied by 10 to the 19. So that's about 2 followed by 19 zeros. Now, I've also seen an approximation that if there was this amount of rice in a pile, it would be the size of Mount Everest. So yeah, that's why the farmer could not get his reward, and he played a bit of a trick on the king. So yeah, exponential growth, a powerful idea. Let's have a look at when x is less than 0. So let's draw another table of values, starting at x equals -1. So let's just write the function down here again. That was 2 to the x. When x equals -1, we would have 2 to the -1, which is 1 over 2. So y is a half. When x is -2, that's 1 on 4. When it's -3, 1 on 8. Then 1 on 16. 1 on 32, and so on. So they are just the reciprocals of these values here. Okay, so now when we go below the left side of the y-axis, we have fractions that are decreasing in size, and they're slowly approaching 0, but they never actually reach 0. So you get closer and closer to 0. Oops. Well, there you go. But it's never actually going to cross the x-axis because, whatever value of x you give this function, you can see it can never equal 0. There's no power of 2 that will make it equal to 0, right? So you could say the x-axis is an asymptote. Of the curve y equals 2x, 2 to the power x. Okay, so that's the function 2 to the x. So we've looked at some examples. We looked at the general shape of an exponential curve. They all generally will look like this. You also need to know how to transform these functions. So we're going to go over to Desmos now. So here on Desmos, I've plotted 2 to the x, and you can see that's got that shape, and it continues. It looks like it's, touching the x-axis. It's never actually going to reach 0 on the y-axis. Okay, so now let's plot 2 to the x take 3. What effect does this have? You can see the graph is translated to the right 3 units. So if we look at this point 0, 1, if I can get it, 1, 2, that's now at 4, 2. I don't know why I can't get these exact points. Yeah, but that's at 4, 2 there. Okay, so that transformation of 2 to the x take 3 is a translation to the right 3 units. Let's have a look at 2 to the 2x. Okay, so we still have that point at 0, 1, but if you look at the point 1, 2 again, you can see that's transformed to a half 2. So this is a horizontal stretch by a factor of a half. And you'll notice these are the same transformations that you apply to the other types of functions, whether it's a polynomial function, a trigonometric, or a reciprocal function. These types of transformations have the same effect. So let's have a look at another one. If we do 2 to the half x, that's a horizontal stretch by a factor of 2. So if we look at this point at 2, 4, that now becomes 4, 4. Okay, so we've multiplied that x coordinate by 2. All right, let's have a look at another one. 2 to the x plus 5. You can see that's a vertical translation up 5 units. So every point on this graph is now shifted up 5. Let's have a look at another example. Negative 3 to the power 10x. Sorry, I wanted to start with 3 to the x and then negative 3 to the 10x. You can see that negative in front of the 3 reflects the function in the x-axis, and the 10 is a horizontal stretch by a factor of 1/10. So let's pick this point 1, 3. And now if you look at the point at negative 3 on the y-axis, you'll see that's 0.1. So it's been reflected in the x-axis, and the x-coordinate, is divided by 10. Okay, then let's look at 3 to the negative x. You can see that's a reflection in the y-axis. And then if we have a constant, 10 multiplied by 3 to the x, that is a vertical stretch by a factor of 10. So this point at 0, 1 becomes 0, 10. You've multiplied that y coordinate by 10. If you look at another point, let's say 1, 3, we'd need to go up to 30. Need to go up to 30 to get that point 130. Okay, back to our notes. So those graph transformations that we applied to polynomials and trigonometric functions and rational functions also apply to exponential functions, and you need to know how to do that. Let's have a look at some examples then. Here we have the function 3 to the x. It says name the transformations and write down the y-intercepts. So we've gone from f of x equals 3 to x to y equals 2f of x. So we're multiplying. Effectively, this would look like 2 multiplied by 3 to the x. So that's that constant multiplying by the function that we just said was a vertical stretch. So vertical stretch by a factor of 2. By a factor of 2. And the new y-intercept would be 0, 2. It's worth, I guess, noting that, so note the y-intercept of y equals 3 to the x is 0, 1. So if you ever have just a constant raised to the x, it will always go through 0, 1. Okay, but then if you transform it somehow, like multiplying it by a constant like 2, then it becomes 0, 2. Okay, what about f of x take 4? This is a vertical translation. And we can use a vector notation for this, 0, negative 4. And then the new y-intercept, if we start at 0, 1 and we go down 4, it would be at 0, negative 3. Okay, then what if we have y equals a half? This should be f of a half x, I apologize. Y equals f of a half x. This is like if you had, multiplied the power by a half. So that's what that notation means, if we had a half multiplied by x in the exponent. Okay, so this was a horizontal stretch. So horizontal stretch by a factor of 2. So notice when it's a vertical stretch, when we're multiplying by a constant, the factor is the constant itself, but when it's in the exponent, when we're doing a horizontal stretch, it's the reciprocal. If you remember that from transformations early on in A-level mathematics, first year as well. Okay, so then the y-intercept, horizontal stretch does not affect the y-intercept, right? So that's at 0, 1. Okay, next example. Y equals ka to the x, passes through 1, 6, and 4, 48. Find the values of the constants k and a. Okay, this is similar to kind of finding the graph of a linear function, right? If you're given 2 points, you can find that the equation of the straight line. So similarly with an exponential function, 2 points is enough to find these constants. So plugging in, let's say using the point 1, 6, we would get y is 6. So 6 equals ka to the power of x. X is 1. Okay, so this gives us, if we rearrange in terms of k is equal to 6 on a. And then if we use the second point, using the point 48, we could then plug in 6 on a. So let's rewrite this out. Y is equal to 48. And then when we get to the k, instead of writing k, we're going to write 6 on a. Okay, so we're replacing that letter there. And then we have a to the power of 4, which is the x coordinate. Okay, now we can cancel the a in the denominator with 1a in the numerator. So therefore we get 48 equals 6a cubed. Then dividing by 6, sorry. 48 divided by 3 is 8. So a cubed is equal to 8, and then a is equal to 2. Okay. And then we can also find k. Given a is equal to 2, k is equal to 3. So there we go. We have k and a. So just a couple of examples there, just to illustrate that you can find these unknown constants given some points on the curve, and you need to know how to transform these. Luckily, they follow the same transformation rules as the other functions we've looked at. And now I want to leave you with something to think about. So far, we have looked at how to differentiate different kinds of polynomials. We've also differentiated rational functions, although not really graphically. We've just kind of, if you're given a function like x to the -3, we know how to differentiate that. And so how do you think we could differentiate a function like 2 to the x? What do you think this might look like? One way you could get started with this is to try to sketch the gradient function. So if you look at different points on this graph, so let's look at the point 1, 1, 2. If you sketch the tangent, what sort of gradient do you think that has? And then that would be your new y-coordinate. And then you could keep doing that, and you could see roughly what the gradient function might look like. And that's one way you could get started with that idea. How do you think we could differentiate 2 to the x? Okay, so that's what we'll be covering in the next video. And then we need to look at logarithms, modeling with exponentials, first, and then logarithms. And so that's the plan. Hope you found this video helpful. Please leave a like if you did, subscribe if you want to see more content. Also join the Discord. The link to the Discord will be in the description if you want help with your homework or help with revision or extra resources. There's a small group of you that pop in there every now and then, which is really cool. So please join the Discord to get extra help. It's completely free, so why not? Okay, Thanks for watching. See you in the next one. Bye for now.